during this session on robust design and Taguchi method, I am going to discuss the topic called quality loss function, as well as the variations of quadratic loss function and average quality loss. So, we will be discussing the three important topics related to robust design and Taguchi method. Okay. So, now we are already aware of that what is the definition of quality as given by Taguchi. So, Taguchi defines the quality level of a product to be the total loss incurred by societal loss, due to failure of the product to deliver the target performance and due to harmful side effects of the product, including its operating costs. So, that means operating cost means that operating processes. That means there cannot be any product which when produced doesn't produce any harmful side effects. Okay, so what you need to do, that is, it is unavoidable. So, you design the product as well as the process in such a way that this harmful side effect comes to a minimum level, that is the minimum, as well as the failure of the product, failure occurrences come down to a minimum level. And if it doesn't fail, okay, or even if it fails rarely, then what do you expect? That the performance product is excellent. And if the performance product is excellent, as well as there is a minimum harmful side effect, we say the quality is excellent. That means what do you conclude? That under these conditions the societal loss is minimum. So, what is the relationship between the quality of the product and the societal loss? That means if the societal loss that you compute, if it is found to be very, very high, you say that the quality of the product is very, very poor. And similarly, if you compute the value of the societal loss, okay, there could be different formulations, there could be under different assumptions, and then you conclude that the societal loss is very, very minimum. Is it okay? And so it is the bare minimum. So immediately you conclude that the quality of the product that you have designed is excellent. Is it clear? So, so you need to do certain calculations, and this the calculation is related to a particular term called quality loss function. Is it okay? So, how do you define the quality loss function under Taguchi philosophy? So, here we have one formulation. Let me explain this formulation. The quality loss function is given as Ly is equals to k times y minus m whole square. Is it okay? But let me first explain these terms which use. What is Ly? Ly is a loss in dollars or in monetary terms when the quality characteristics is equal to y. It is the average quality loss incurred by the customers. That means in a continuing running continuously running production system, given a particular product or given a particular component on a particular process, what you find that you start producing a particular component in large numbers. So, there will be many units, and obviously against a particular unit you measure the value of the quality characteristic. So, that value is y, and obviously this y is a random variable. Now, what is so that is why we say that y is the value of the quality characteristic, which is a random variable. For example, this could be the length, this could be the width, concentration, surface finish, flatness, etc., etc. That means these are the variables, and we have already defined what is a variable quality characteristics, that means they are measurable, and the exact the value will be known. Now, what is m? M is the target value of y, and what is k? K is the constant called quality loss coefficient. It's fine. Now, how do you explain it? That means what we say, that the loss is proportional to the square of the deviation of y from the target value. So, this is the square of the deviation. So, obviously it is proportional. So, the when you write say when you consider the proportionality constant, the equation becomes Ly equals to k times, that is the proportionality constant, into y minus m square. So, this is the Taguchi's assumption, and it is a quadratic loss function. It is a quadratic loss function. What actually he has assumed, that means he has assumed quadratic loss function. He collected data from several say the products, and ultimately you will find in majority of the cases, that means this loss function is may be considered to be a quadratic loss function. Is it clear? So, this is the formulation of say the loss, or the societal loss, or the quality loss. Okay. So, quality loss function. Now, how the values of say the quality loss function, that is this one, is related to the value of k. Is it okay? So, as you find that if the value of k increases, is it okay, say from k equals to 1 to k equals to 5, what could be the shape of the curve? So, shape of this curve, the shape of this curve, is it okay, quadratic loss function will be very, very stiff. That means, if suppose this is your the target, so if there is the deviation from the target is more, that means the loss you incur will be very, very, very high. Is it okay? And this is a non-linear function, definitely. So, this is, and similarly, suppose on the other side, suppose you have say the deviations on the other side. Is it okay? So, all these values are possible. What you find, again you are incurring a loss, because this is a square term. So, whether it is a positive deviation or the negative deviation, the impact remains same. Is it okay? So, this is just a pictorial representation to know how the value of k is affecting the corresponding loss. Now, whenever you say that this is the target value, and suppose the target, from the target there is a deviation of plus delta on one side and the deviation of minus delta on the other side. Now, this is a quadratic loss function. So, what do you expect? That if the deviation is plus delta from m, then the corresponding loss is A, capital A. Is it okay? So, capital A refers to the quality loss, and if the deviation is minus delta, that means the value you get, that is m minus delta, and again is a quality loss function, the effect remains same. So, the corresponding loss you incur, that is A, right. And what the Taguchi has pointed out very clearly, that whenever you try to compute this loss, it is always better that you compute this loss in monetary terms, so that everybody's interpretation of the loss may be almost similar. Is it okay? So, so always there should be a money attached to this loss function. So, a convenient way to determine k, how do you determine the proportionality constant, that is k? So, you determine k first. To determine k, what you need to do? First, you need to determine the functional limits for the value of y. Is it okay? That means there will be range of values of y, okay, which is acceptable to you. It's clear. It's not that any value of y is acceptable to you. That means you know what is its impact. You say yes, with this range of value, you can expect performance from the product or the performance of the component. Is it okay? So this range is technically feasible. Functional limit is the value of y at which the product would fail in half of the applications. Is clear? So let m plus minus delta be the functional limits, as we have already pointed out. Suppose the loss at m plus minus delta is capital A, I have already mentioned. Then by substitution in equation 1 we have small k equals to capital A divided by capital delta square, where A is the cost of repair or replacement of the product and includes the loss due to the unavailability of the product during the repair period. Is it okay? So, so you must be able to, so there could be the certain points to be remembered why with respect to a particular process while you compute this quality loss, like say the repair cost you must know, replacement cost you must know. Similarly, in the cost due to unavailability, so these cost elements, so the corresponding data you must have. Is it okay? At least there will be good estimates of all these cost elements. Okay. So related to the kinds of loss, that means what you need to do, that means you need to define in explicit terms in a given condition what are the loss related components, what are the loss related elements. Is it okay? So these are just an examples. So when capital A is known, okay, and corresponding the deviation is also known, that is the functional limit, obviously you can have an expression for small k or the proportionality constant. Okay. So obviously the loss expression for loss becomes capital A divided by capital delta square into y minus m square. Is clear? So this is the quality loss function. Now I have already mentioned that as far as quality characteristic is concerned, this quality characteristic can be classified under three categories. What are those? First one is the target is best or the nominal is the best. That is first type. What is the second one? Second one is the smaller the better type characteristics. And what is the third one? Third one is the larger the better type characteristics. Now in the previous case, when we propose say the loss function, the quadratic loss functions, what we have assumed that the quality characteristic chosen is of the first type. That means it is of say the nominal is the best type or the target is the best type. Is it clear? Now let us talk about the smaller the better type characteristic, quality characteristics. Some characteristics have the ideal value equal to 0 and has their value, and as their value increases the performance is poor. Is it okay? That means if it becomes non-zero and the positive, then and as this value increases, that means the deviation from 0, what happens? That means the loss you incur is increases. Okay, so the loss will be very high if the deviation from 0 is large. Such characteristics are called smaller the better type quality characteristic. Is it right? There are many examples. I have already mentioned those examples, so please refer to those examples of this type of quality characteristic. The quality loss in such situations can be approximated by the following function, which is obtained from equation 1. Again you refer to equation 1, and here your target value is 0. Is it okay? Equal to 0, we have already mentioned. So hence this is Ly is equals to k into y square. This is just an application of the previous case when m becomes 0. This is a one-sided loss function since y cannot be negative. Is clear? The quality loss coefficient k or the proportionality constant can be determined from the functional limit, like we have done in the previous cases, and the quality loss A0 can be determined at the functional limit by using equation 4. Is it clear? That means the functional limit value is known and corresponding loss also you have estimated. So these two values are known. Obviously you can get the value of k. Okay. So this is the second case. In the third case, that means when you refer to larger the beta type characteristics, some characteristics do not take negative values, and as their value becomes larger, the performance becomes better. Is it okay? Like say, the tensile strength of a component. Okay, so you specify the minimum value, say 3000 kg. Okay. Now, what you may feel that any value greater than 3000 kg is greater, whatever may be the square area. So that is the sectional area. That is, the quality loss becomes smaller. Their ideal value is infinity, and at that point the loss is 0. Is it okay? That means it is the larger the beta type, right? Such characteristics are called larger the beta type quality characteristics. It's clear. Like say, in a typical service organization, the service quality should be as high as possible. Is it okay? So, so theoretically speaking, larger the beta type characteristics, that means the value which you have in your mind of say the quality service could be it may go up to the infinite level, theoretically speaking. So there are many such examples. The loss function for a larger the beta type characteristic is obtained by substituting 1 upon y for y. Is it okay? So that's why this is Ly equals to k into 1 upon y square. Is it okay? So k upon 1 upon y square. To determine the constant k for this case, we find the functional limit delta below which more than half of the products fail, and the corresponding loss is capital A. Same notations we have used. Is it okay? Substituting delta and A in equation 5, that equation 5 is Ly equals to k into 1 upon y square, and solving for phi, we get k equals to delta A into delta square, capital A into delta square. Now, there is another case, like say we are referring to say the quality loss function. Now, there is one particular case that also I would like to highlight, that is called asymmetric loss function. In the previous case, that means the first case when you refer to, what we have assumed that even if there is a deviation on the positive side or is a deviation on the negative side, like m plus minus capital delta, you will find that the impact is same, and that the impact in terms of the loss, that is the capital A, we have assumed. That means it is a symmetric case. That means the effect of positive deviation is same as that of the negative deviation. Now, this is a symmetric case. Now, there could be cases where it may not be symmetric, it may be asymmetric. So whenever you refer to that kind of quality characteristic, then we should be will be referring to the asymmetric loss function. So how do you define this asymmetric loss function? So what we have mentioned, that in certain situations, deviation of the quality characteristic in one direction is much more harmful than in the other direction. Is it okay? Much more harmful means in one direction with the same amount of deviation, as the magnitude is same, you will find that the loss is very, very high. Whereas on the other side, even if the deviation magnitude remains same, the loss may not be that high. Is it okay? So in the other direction, either in one direction positive or negative, so in that case the opposite will be negative or positive. In such cases, the quality loss would be approximated by the following asymmetric loss functions. That means instead of having one loss function, that is k into y minus m square, now this one loss function is split into two. Is it okay? So the first one is when y, the actual value, is greater than the target value, you have k1, that is the proportionality constant, into y minus m square. So this formula you will be using. and when y is less than equals to m, is it okay? Then you will be using that second formula, that is k2, that is the proportionality constant into y minus m square. Is it okay? So this the four cases we have explained with the help of say the figures, and look at these figures, you will get an idea about the variations of the quantity loss function. So here the nominal is the best case, we have already explained. M is the target value or the nominal value. Nominal value means the desired value, and if the deviation is m plus delta on this side and m minus delta on the other side, you will find it is a symmetric loss function. That means the loss you incur, that is capital A, remains same. Then the smaller the better, that means the target value will be 0, that means this is shifted to the left. Is it okay? And you reach here 0. Is it okay? So if there is a deviation of delta, you incur a loss of capital A. Okay, we are always saying that better this y axis must be in means the unit of measurement of A, or the loss in general must be a monetary unit. Third case is the larger is the better, larger the better quality characteristics. So if it is very high, that is okay, you will find that it tends to infinity. It tends to, the loss will be 0, loss will be 0. And if there is a deviation from the other side, that is delta, you will find you are incurring a loss of A. Is it okay? So correspondingly, the difference from 0 you calculate and you find that the loss is capital A. So this is a symmetric case. Now you move to the asymmetric case, asymmetric loss function. So here m is the target. Now if there is a negative deviation, you will find that the impact is very high, that means loss is very high. Whereas if there is a positive deviation, like say impact is not that high, but still there is substantial loss due to a deviation of plus delta from m. Is it okay? So these are the four cases we come across. Now the performance of a product varies in the field due to causes known as noise factors. The noise factors are classified as external, unit to unit variation and deterioration. Is it okay? We have already mentioned all these three factors. The environments in which a product is operated and the load to which it is subjected are the two major external sources of variations of product's performance. Just we are recapitulating in fact, and always when the Taguchi method, when you opt for say robust design, make sure that the impact or the effect of external as well as the internal noise factors is held at minimum. The variation that is inevitable in a manufacturing process leads to variation in the product parameters from unit to unit. These examples already we have given. When a product is sold, all its functional characteristics may be on target. As time passes, however, the values of the individual components may change, leading to deterioration in product's performance. Okay. So how do you compute the average quality loss? So for computing average quality loss, what you need to know, you need to collect data. Okay, that means you need to collect data on y, and when you collect data on y, and you know what is m, and you know what type of quality characteristics you are dealing with, so you will be able to calculate the average or expected quality loss. So the quality characteristics y of a product varies from unit to unit and from time to time during the uses of the product due to noise factors. So this is basically the variation. The variation, this is basically a distribution of the values which you get, distribution of y with mean mu and variance sigma square. So this is mu and the several values you have collected. Say 1000 such data points you have collected, 1000 say the values of say y you have collected, and what you assume that there is a distribution. That means there is no impact of say assignable causes. So the system is free of assignable causes, or the system is only affected by the external noise factors. Okay. So this is the data you must be able to collect. So how do you calculate the average quality loss? That means this is so average quality loss. That means n number of data points you collect. So y1, y2, yn for the quality characteristics y taken on a few representative units throughout the design life of the product. Let y be a nominal the best type quality characteristics and m is the target value. Then the average quality loss is computed with this formula. Is it okay? That means 1 upon n expected value, loss of y1, loss of y2, loss of yn, and then you apply the formula, that is the k is a proportionality constant and this is the squared terms, and when you have two expressions, you have k into mu minus m square plus n minus 1 by n into sigma square. Okay. Unbiased estimate you calculated, and mu and sigma square are the mean and the variance of y respectively. I have already mentioned. So ultimately mu, the expression is this, and the sigma square is this one. Okay. An unbiased estimate. When the number of measurements n is large, that means this is the q, the quality loss is k into mu minus m square plus sigma square. Okay. So this is transformation. So average quality loss has the following two components. The first component is this one, k into mu minus m square, resulting from the deviation of the average value of y from the target, and k into sigma square, resulting from the mean square deviation of y around its own mean. Is it okay? So the first component is easier to eliminate, and the second component, reduction, needs decreasing the variance. So that is the challenge in fact. Like I have already mentioned, that any exercise on quality is essentially an exercise on say the variability or the variance. So these are the again if you refer to this particular table. So in this table, what you have noticed, that depending on the type of quality characteristics, the loss function is shown. Is it okay? And the mean square deviation is also shown, mean square deviation MSD. Okay. The sample variance plus y dash minus m, this is the mean and this is the target value. An average loss function, the expression for the average loss functions are given, and similarly the smaller is the best, larger the better. So all these cases we have shown. So average quality loss. So what you need to do, you have to screen out the bad products, identifying the cause of malfunction and eliminating it, and application of the robust design method. So the method involves in making a product's performance insensitive to noise factors. Is it okay? So these are the actions you have to take, and then what you need to do, that means once you are aware of these actions or the corrective measures, then possibly both the variability is reduced as well as the target value you can achieve, and then what you find that for the majority of the points or for majority of the values you get, and the quality loss, whatever the relevant formula you use, with which you use this quality loss, the quality loss in monetary terms is held at the minimum level, and you say that the objective of using Taguchi method is fulfilled. But this is just one step. There are many other steps you have to follow, and those other aspects we will be discussing in the subsequent lecture sessions.